Hello friends, the topic for this video is Dijkstra's algorithm for finding the shortest path. Given a graph G with set of vertices V and set of edges E, Dijkstra's finds the shortest path from a given source vertex, let's say S, the source vertex S, to all other vertices in a graph. It will find out the shortest path from S to all other vertices in a graph. Given that this graph is a weighted graph, meaning each edge is given a weight like this. It can be a distance between two cities, it can be a cost of traveling from city T to X, it can be anything, but the weight is given and all the weights are non-negative. All these values should be non-negative. This is the assumption for Dijkstra's. Now it has wide variety of applications. If you have used Google Maps for finding the shortest path or finding the distance from the source to destination, you may have seen something like this, where it will give you various different alternative routes for going from source to destination, and it also finds out the shortest path for you. So this is the problem that Dijkstra is trying to tackle. Even in computer networks, there's something called as router, which actually routes the packet. This is the incoming packet, and this packet has to go to some destination computer. Let's say this is a destination computer. This router can decide from which path the packet will traverse. Okay, it will choose the path which is the shortest from the source, from the router to the destination router. Now to implement Dijkstra's, we will be using two data structures, two sets actually. One is set S, which will contain all the vertices for which the shortest path has already been determined. Okay, there are total V number of vertices. S contains all the vertices for which the shortest path is already determined, and Q contains all the vertices for which the shortest path is yet to be determined. Obviously, Q would be V minus S. All the remaining vertices apart from S is there in Q. And Q, I have given the name Q because Q generally is a priority queue. Okay, if it's a priority queue, you need to have a key value for the priority, for deciding the priority, and key value is nothing but the distance value, that is the distance from source to that particular vertex V. Okay, we'll come to this while executing the example. So initially, to start up with, the set S is empty because we have not visited any node as of now. Nothing is being determined, nothing has been processed initially, and Q contains all the vertices in V because nothing has been processed initially. So this is the initial setup. Let's assume this graph for which we are trying to find out the shortest path from the source S. This graph is given to us, and let's say this S is our source. That means we are going to find out the shortest path from S to T, S to Y, S to X, and S to Z. And as I have told you initially, the set S is empty because nothing has been determined, no shortest path has been determined, so S is empty. And Q is a minimum priority queue. It has all the vertices in V, so there is S, T, Y, X, and Z. Alright, now because this is a priority queue, we have to give a priority for each element or the key value. The priority or the key value for each element is written here. Okay, so key value is nothing but the distance from the source to that vertex V. Alright, so let's say that for T, we do not know what is the distance, shortest path from S to T as of now, so we'll assume that it is an infinite value. It's a very big number. We do not know what is the distance as of now, so we mark it as infinity. Similarly, S to X infinity, X to Z infinity, S to Y also infinity. So this I am maintaining in a distance array from S to T infinity, S to Y infinity, infinity, and infinity. But for the source vertex itself, going from source to source is obviously 0. So I'll mark the key value of the source as 0. For all of the vertices, it is marked as infinity. Alright, And suppose I found out the shortest path from the source, let's say u, to the source v. Then if I find out the shortest path, I'll mark that in red color. That edge will be marked in a red color. These are the color coding that I'm using in an example that will follow. Okay. If I find out the shortest path from u to v, I'll mark it in a red color. Okay. And now I need to store who is the parent of v, right? The parent of v here is u. So all the parent nodes, I'll be storing it in a array called as parent. Initially we do not know who is the parent of each node, so I'll mark it as null or nil. Okay. So all of them are nil. The parent of all the nodes are nil. Okay. And if I have a gray colored vertex, that means this vertex is with the minimum key. So in this example, all the key values are infinity except the source, which is 0. So the minimum key is s, therefore s is marked as gray in color. That means it is under process. If I have a vertex in green color, that means this vertex is in set S, that means it is being already processed. Okay, this vertex is already being visited if it is in green color, and if it is in white color, it is yet to be processed. So this is the initial setup. Now we'll begin with an example. So let's take this same example. So initially the set S is empty and Q is having all the nodes in a graph, and the distance for S is 0, for all other vertices are infinity, and the parent of all the nodes are nil for now. So first thing first, what you do is, first thing is we need to extract mean. So I have told you that we are going to implement Q as a priority queue. So this would be a minimum priority queue, because we are going to give a priority to the minimum value, because we are trying to find out the shortest path. So this is a minimization problem. Therefore we are going to find out the minimum distance from the source to the destination. Now extract mean will extract the vertex with the minimum key value from the given set of vertices. Okay, let's say that vertex is u. Okay, let's say u is minimum, the vertex u is minimum. Now I'll see what are the neighbors of u, what are the outgoing paths from u. All the neighbors of u, let's say this is v1, v2, v3. So I'll for all the neighbors of all the neighbors of u, okay, let's say the neighbor is marked as v, v1, v2 and v3. I'll find out if I can update the distance. If I go via this path, do I get a shorter distance? If I get the shorter distance, I'll update the distance. I'll come to this while you execute in the later slides, but this is the idea. So I need to repeat this entire thing for all the nodes. So now in this, if we apply extract mean, I'll find out the node S is extracted from the queue. So node X is removed from the queue. Let's see how it happens. So S is removed from the queue and put in the set S. So queue does not contain S now, it is now moved to the set capital S. Alright. So this is already being visited, so processed, so it is marked in green color. And now I need to do something called as relaxation. Meaning now I'll have to find out all the outgoing link from S to all other neighbors. So S has two outgoing links. One is to T, the distance is 10, and one is to Y, the distance is 5. So if I go from S to T, initially it was infinity. I marked the distance as infinity, but if I go via S, going to S is 0, so 0 plus 10 is 10. 10 is less than infinity, so I'll update the key, the distance of T to 10, because 10 is less than infinity, and I'll mark S as the parent of T. So for T, the parent is S, and this is marked as 10. Similarly for Y, previously it was infinity, and now I get a new distance. 0 plus 5 is 5, so 5 is less than infinity, so I'll update this to 5. Okay, and the parent of Y is nothing but S. This is what I do. Now this is I've executed it once, so I need to repeat this for all other nodes. Now what I'll do is, now again I'll find out the minimum. I'll do extract min. Now from all the nodes except the green one, which is already been visited, the minimum value is, this is 10, infinity, 5 and infinity. So if I extract min now from the queue, I'll get, if I extract min from the queue, I'll get y, because y is having the minimum key value, that is 5. So y is marked in gray color. Now I'll see all the outgoing links from y. So from y to t, y to x and y to z, right? So I'll see going till y, from source to y is 5, distance is 5. If I go from y to t, 5 plus 3, it becomes 8, right? And 8 is less than 10. Previously it was 10, now I get 8, which is less than 10, right? So I'll update for t, the distance is 8, for t the distance is 8, and the parent is, it's coming via y, so y is the parent. Similarly, from y to x, s to x, actually I am trying to find out the path from s to x. So s to y is 5, so 5 to, these are visited, okay, these are already done. So from this to this is 9, so 9 plus 5 is 14, 14 is less than infinity, so I'll update the distance of x to 14, okay, and the parent is obviously y, it's going via y. Similarly, for the next neighbor, that is z, s to y is 5, so 5 plus 2 is 7, 7 is less than infinity, okay, so I'll update it to 7 and the parent is y. That's what I'm done. So I've updated the distance and the parent. Now again I'll find extract min. Now do not consider this, out of all remaining, these 3, which is minimum? 8, 14 and 7. 7 is minimum, so z is minimum, right? Now I'll find all the outgoing links from z. From z I have 2 outgoing links, one is to s, but s is already been visited, so I'll ignore this outgoing link. There's one more outgoing link to x. So if I, previously the distance for going to x was 14 via this path, 5 plus 9 was 14. But if I go via this path, 7 plus, till here it's 7, 7 plus 6 is 13. So 13 is less than 14, so I get a better shortest path, that is 13, so I'll update. So to x it is 13 now via z. That's all. Now again I'll do extract min. So out of this remaining 2, the minimum is 8 and 13, the minimum is 8. So I'll find all the outgoing links from t. So t has a link to y, but y is already visited, so I'll ignore y, ignore this link. And from t to x, previously it was 13, okay, for going to x, shortest path was 13 from source, so it was 5 plus 2 7, 7 plus 6 13, but if I go via t, 8 plus 1, it becomes 9, so 9 is less than 13, right? So I'll have to update. To go to x, I can, the shortest path is 9 via t, I go this path. Alright, now I'll extract min. If I extract min, I'll extract x, because this is only remaining one, okay. Do I find any outgoing link? Outgoing link is to z, but for z already the path has been determined, so that's all. I also visit x and I'm done. My queue is empty now, and so I'll stop. And this is the shortest path from the source s to s, it is 0, s to t it is 8, okay, s to y is 5, s to x is 9, s to z is 7. Alright, and you may be wondering why we stored this parent. It's only to trace back the path. If you want to trace back the path, you will be needing the parent. So if I want to find out the shortest path from s to, let's say, x, how do I go to x from s? So I'll see for x, who is the parent of x is t. So to go to x, first I have to, the immediate parent of x is t. Who is the parent of t? The parent of t is y, y to t. Who is the parent of y? Parent of y is s, s to y. So the path from S to X is S to Y, Y to T, this one, and T to X, that is marked in red color. So this makes 5 plus 3 is 8, 8 plus 1 is 9. So to trace back the path, you will be needing the parent array also. Now let us quickly look at the pseudocode of Dijkstra's. So given a graph G, a set of weights W and the source S. What we do initially is, for all the nodes, we'll mark the distance as infinity, right? And the parent of each node we do not know. So let's say the parent is marked as nil. That we have already seen in the initial setup, right? Let's say the source, this is the source. For the source, obviously the distance is 0, and we'll initialize the empty set S, and Q is my priority queue, wherein I'll put all the vertices. Okay, this is the initial setup. Okay, now I'll repeat something until my queue is not empty. If queue is empty, I'll stop. So this is the while loop. First thing what I'll do is I'll extract the minimum. I'll extract the minimum from the priority queue. So let's say U is the minimum. And for all the neighbors, V of adjacency of U. So I'll find all the neighbors of U. Okay, let's say the neighbor is called as V. Okay, for all the neighbors, I'll see if I can update the distance. So let's say the distance for this is, let's say this is V1, V2, V3. Let's say this is V1 dot D, already existing distance. Let's say it's coming from some other node. Let's say X. This distance is coming from this node, let's say. Now I would like to see if I have a better path from U to V1. So what I do is I'll see the distance till U. So there are other nodes connected to U. So distance from source to U is U dot D. So U dot D plus the weight from U to V. So weight from U to V1. If this entire thing, this plus this weight, if this entire thing is less than this, then I get a better path. Therefore I need to update the distance of V1, and I need to mark U as the parent of V1. That's what is done here. If the distance of V is more than the from U, the distance till U from the source, and from U to V, if this entire thing is less than this one, so I need to update the distance to V from the source as U dot D, that is distance from source to U plus the weight from U to V, and I will mark U as a parent of V. So I'll keep on repeating this process until I am done. At the end, I'll find out the list with all the shortest path. Okay, let's see how to analyze the time complexity of Dijkstra's. Okay, now Dijkstra's can be implemented using an array. If you implement Dijkstra's using an array, minimum priority queue just using a plain simple array, then let's see what is the time complexity. Obviously, for this for loop, there are V number of vertices, so it's order of V. Okay, this order of V. For initializing, it's a constant task. Okay, this is a constant task. For initializing a queue with all the vertices, again V number of vertices, so it's order of V again. This loop will run until I am done with all the nodes. So again, this loop will run for n times or n number of nodes or V times. So this is order of V. And extract mean. So in a given array, if you just, it's a simple array, a 1D array. So if there are V number of nodes, to extract the minimum will take order of V. If there are n number of elements in an array, to extract the minimum will take order of n. So it's order of V to find out the minimum. This is order of V finding out the minimum, plus order of V plus This is adjacency. So for all the outgoing edges from u to v, okay, so let's say there are e dash number of adjacent edges from u to v. So e dash, order of e dash, and this is a constant time, order of 1. So e dash into 1 is e dash. So order of v plus order of e dash into order of v, because this is inside a while loop. Okay, so this order of v plus order of v plus order of v into v is order of v square, plus order of v into e dash is order of v into e dash. So these are all outgoing edges, okay, from any given node, and there are v number of vertices. Let's say E1 is all outgoing edges from node u, E2 is all outgoing edges from node, let's say v. So similarly, for all the nodes, if the outgoing edges are given, if I add them together, I'll get is nothing but is equals to total number of edges. Similarly, so if e dash number of edges are there, average number of edges is e dash from any vertex. So v into e dash is nothing but e, which is total number of edges. So v into e dash is e, okay, and now if I add v plus v square plus e, so highest order is v square. So we say that asymptotically the time complexity is order of v square, which is pretty big number. This can be improvised by using a binary heap. If you implement a minimum priority queue using a binary heap, so for this you need to understand what is a binary heap, right? So if you use a binary heap, this is not changed. This is order of v itself, this is order of v itself, this is order of v itself, but extracting minimum now would take only log v time. This is improvised, okay, this is e dash, and this is, now for doing this is not a constant time, because this is implemented as a decrease key operation in a minimum priority queue implemented using a heap. So this can be implemented using decrease key, which takes log v time. Okay, so to understand all these things, first of all you should understand what is a binary heap. All right, so log v time, so total is v plus v, v into log v plus e dash log v. Okay, so this is v log v plus v e dash log v. We know that v into e dash is nothing but e, so v into e dash is e, so this is nothing but e log v, this is v log v, v. Out of all these things, this is of the highest order, e into log v, so the time complexity is e log v. All right, and this can be actually further improvised if you use something called as Fibonacci heap. This is a bit advanced topic, but if you use Fibonacci heap instead of normal binary heap, it would be done in order of v log v, a bit improvement than the previous one. All right, so this is the overall idea of what is Dijkstra's, how to implement and how to analyze the time complexity of Dijkstra's. To implement it efficiently, you should know what is a minimum priority queue, how to implement minimum priority queue using a binary heap. Okay, then you could implement this algorithm as it is, and it should work for you. If you have any doubts in this particular video lecture, you can comment on this video. That's all for today. Thank you.